Our entire world, it's pretty much built on concrete. So what happens when the very foundation of modern life starts to crack? We're about to dive into how a tiny, almost invisible problem can have these massive, massive consequences, and how a whole new way of seeing things with AI might be our best shot to catch it in time.
It's a huge question, right? Whether you're talking about medicine or security or engineering, the biggest threats are so often the ones that are just impossible to see until it's way too late. Well, today, we're talking about a threat that is literally etched into the surface of our cities.
Yeah, you heard that right. The bridges we drive across every day, the buildings we work in, the dams holding back entire rivers, all of them are vulnerable. And these cracks, no matter how small they start, they're a really serious warning sign.
Okay, so first things first, let's really get a handle on the scale of this problem and why the old school way of looking for these cracks just isn't going to cut it anymore.
So look, this isn't just about things looking a bit worn down. These cracks directly impact the safety and the durability of everything around us. For decades, the only way we could find them was to send a human inspector, often into some pretty risky situations, to visually check every single inch. I mean, that process is incredibly slow, it's expensive, and let's be real, it's super prone to human error.
So obviously, we needed a better way, a much better way. So how do we make the leap from relying on the human eye to actually teaching a machine how to see?
For a long time, we tried using basic computer vision, things like edge detection. And it was an improvement for sure, but it really struggled with tricky backgrounds or different lighting. The real game changer, the moment everything shifted, was in 2012 with the deep learning boom. All of a sudden, we had a tool that was powerful enough to truly automate this critical job.
So how in the world do you actually teach an AI to see a crack? Well, it turns out it involves some pretty incredible tech and a really, really clever shortcut that researchers used to get amazing results and fast.
The technology is called a convolutional neural network, or CNN for short. Basically, you can think of it like a digital brain that's kind of modeled after how our own eyes and brain work together. It's built specifically to find patterns in pixels, which makes it incredibly good at figuring out what's in a picture, whether that's a cat, a car, or a crack.
Okay, but here's the catch. Training a powerful CNN from scratch takes millions and millions of images and just a massive amount of computing power. The researchers behind this work, they didn't have that, so they had to get clever.
They used this amazing technique called transfer learning. And the best way to think about it is like this. Instead of teaching an AI from day one what an edge is, or a texture, you take a model that already has a PhD in image recognition, one that's been trained on millions of photos. It already knows cats, cars, trees, you name it. You're just giving this expert a brand new, super specific job. Find the unique visual signature of a crack.
So here's the play-by-play. You take a powerful, pre-trained model. Then you basically snip off its final decision-making layer. That's the part that would say cat or dog. You replace it with a new, much simpler layer that only has to answer one question: crack or no crack. Then you just fine-tune it with a much smaller, specialized set of concrete pictures. It's just wildly efficient.
But hey, even with a shortcut like that, more data is always king. So what do you do if you can't go out and take thousands of new photos? Well, you use another clever trick. It's called data augmentation. And what you're basically doing is showing the AI the same image from every possible angle, turning one picture into many, many learning opportunities.
First up, you flip it. The AI sees this as a brand new image, and it learns that a crack is still a crack, even if it's mirrored. Next, you rotate it. This is super important, because it teaches the model that cracks can show up at any angle. And then you shift it around so the AI learns to spot a crack, even if it's not perfectly centered in the frame. With just these simple tricks, you can multiply your dataset and build a way smarter model, all without taking a single new photograph.
Okay, so this is where it gets really cool. The researchers didn't just build one model. Oh no, they set up a competition, pitted several top AI models against each other, like a bake-off, to see who was the absolute best for this job. So, they basically put 4 well-known models into the ring, tested them all on the exact same dataset. And the goal wasn't just to find the most accurate one, it was to find the one that gave the absolute best balance of accuracy, size, and speed.
So let's look at the tail of the tape for the two main contenders here. On one side, you've got DenseNet 201, the heavyweight champion. It's a beast, incredibly accurate, but it's massive in size, which makes it slow and hungry for resources. And on the other side, you have EfficientNet B0, the welterweight. It was literally designed for efficiency, to get the most bang for your buck in terms of performance versus size. And here are the results. Just look at this scorecard. Sure, DenseNet 201 has the highest accuracy, but only by a teeny tiny fraction. Now look at the model size. I mean, it's over 70 megabytes. That's huge. But our welterweight, EfficientNet B0, gets a jaw-dropping 99.11% accuracy in a package that's less than a quarter of the size. That, my friends, is the definition of efficiency.
Seriously, let's just let that number sink in for a second. Over 99% accuracy. That means this AI is nearly perfect at spotting whether a piece of concrete has a crack or not. And that is the key takeaway here. EfficientNet B0 was the hands-down winner because it hit that perfect sweet spot. It's unbelievably accurate while being small and fast enough to actually be practical out in the real world.
Okay, so what does this all actually mean for us in the real world? Why does having a smaller, faster, but still super accurate model matter so much? Well, it matters a ton because a small model like this can run on a simple smartphone or on a drone, not some massive supercomputer. That makes this kind of inspection accessible and affordable for everyone. It means we can scan our infrastructure constantly, catching problems way earlier. And all of that, at the end of the day, means safer bridges, safer buildings. It can literally save lives.
And you know what? The work is far from over. The researchers themselves said it best. The next step isn't just seeing if there's a crack, but understanding how bad it is. How wide is it? How deep? That right there is the next frontier for this kind of technology.
Which really leaves us with this one big, powerful question. We've just taught a machine how to see a flaw in concrete. So what else is out there, hiding in plain sight? What other critical, invisible problems in medicine, in our environment, everywhere, could we finally solve just by teaching an AI how to look?